Ever tried to measure something really tall, like a mountain, using just like a tape measure?
You'd need a really long tape measure for that.
Yeah. Yeah. Not exactly practical, right? But what if I told you there's a way to figure that out using nothing but, well, triangles?
Triangles.
Triangles. That's the beauty of trigonometry.
It's true. It sounds a little abstract when you talk about all those formulas you find in textbooks.
Right.
But it's a really powerful tool for understanding the world around us, especially when we're talking about distances and heights that just seem impossible to measure directly.
Exactly. And that's exactly what we are going to be diving into today. We're taking a look at a fascinating section all about real-world trigonometry applications. You might not think that a textbook section on this would be a page-turner, but trust me.
I mean, who doesn't love a good practical application of math?
Exactly.
Yeah.
And this one is really fascinating. Once you start to see these principles in action, you're going to start noticing triangles everywhere you look.
I think you're right. It's like you unlock this hidden dimension where everything you look at, you're like, oh, there's a triangle. I could probably figure that out
Exactly.
if I had my trusty protractor and my calculator.
Exactly. So let's start by kind of breaking down what is trigonometry? What are we even talking about here?
Yeah, so at its core, trigonometry is all about understanding the relationships between the angles and the sides of a triangle. And, these relationships, they just pop up constantly in our three-dimensional world. So it gives us this really cool way to kind of calculate those distances, those heights, the things that are literally out of reach.
It's like we can't always get on a ladder or climb to the top of that mountain
Exactly.
to get that measurement, but we can use these other tools.
Exactly.
Speaking of out of reach, this deep dive mentions a really amazing feat of trigonometry. It's the Great Trigonometric Survey of India. Have you heard of this?
I have heard of this. This is a very, very cool example. So these folks were mapping the Himalayas back in the 1800s.
Wow.
Long before we had satellites or lasers or anything like that. And they used these massive instruments called theodolites.
Okay, so for our listeners who, like me, are picturing something out of like a pirate ship or something, what is a theodolite?
Yeah, so the theodolite, basically it's a tool that measures angles. And you're not wrong to think pirate ship because they were used in navigation.
Oh, okay.
But these were land-based. And these were huge. These were like the biggest theodolites ever built. And the fact that they could use these instruments to accurately survey such challenging terrain.
Like the Himalayas?
Like the Himalayas, yeah. Eventually led to the discovery of Mount Everest.
Wow.
So it's a testament to both the power of trigonometry, but also human ingenuity.
Yeah. Before we get too far into the thick of it, let's just make sure we're all on the same page with a few key terms. So imagine you are looking at something in the distance, okay? That imaginary line from your eye to that object, that's what we call your line of sight. And picture another line. This one's extending straight out from your eye, but parallel to the ground. The angle between that horizontal line and your line of sight, when you're looking up at something,
Okay.
that is your angle of elevation.
Okay.
Does that make sense?
It does. So if you're like looking up at the top of a building,
Exactly.
that's your angle of elevation.
Yes.
Okay.
And conversely, if you are, let's say, on top of that mountain we were just talking about and you were looking down, the angle formed between your line of sight and that imaginary horizontal, that's called the angle of depression.
Angle of depression.
Okay.
Got it.
We've got lines, we've got angles.
Right.
But how do those actually help us measure anything? Well, this is where the magic of trigonometric ratios comes in.
Ah, yes. The ratios.
Specifically, we're going to talk about the tangent, often shortened to just tan. Now, before you click away, don't worry, we're not going to go diving into any complex formulas here. But the tangent basically gives us a relationship between an angle and the lengths of two sides of a right triangle.
Of a right triangle. Okay. So we're talking about those triangles where one of the angles is 90 degrees.
Exactly. A right angle.
Okay.
And so by knowing just one angle and one side length, we can use the tangent to unlock all the other ones.
So it's like a key.
It is like a key. It's like a mathematical key.
A mathematical key to unlock the secrets of the triangle.
Exactly. Okay, so let's see this in action. Imagine you're standing, let's say, 15 meters away from a tower, and you want to know how tall it is.
Okay. A very practical problem. We've all been there, right?
You whip out your protractor.
Of course. Always have it on hand.
Because who doesn't? You measure the angle of elevation to the top of the tower, and let's just say it turns out to be 60 degrees. Now what?
Okay, so this is where things get really neat. We have an angle. We know the angle is 60 degrees,
Mm.
and we know the adjacent side, right? That 15-meter distance you are from the tower,
Okay.
the tower's height, that's the opposite side. And that means we can use the tangent, right? Because tangent is opposite over adjacent.
Yeah.
And the great thing is, the tangent of 60 degrees, that's a known value.
Right.
That's the beauty of trigonometry.
It's already been figured out. We don't have to do that complicated math.
Exactly. Someone's done that for us.
Bless them.
We can just look it up. And by plugging in that value along with our known distance into, again, a very simple equation we can solve for the tower's height.
So it's like we're solving for x, but instead of just an x, it's the height of a tower.
Exactly.
I like it. But it's not all about towers, is it?
No, not at all.
Like this has practical applications too.
Absolutely. Even something as simple as, let's say, an electrician who needs to fix something on an electric pole.
Uh-huh.
They're using these same principles.
Mm.
It's kind of like having a superpower.
Right.
You walk down the street, you look at a building, and you think, I bet I could figure out how tall that is.
Yes.
With just like a few little measurements and a little bit of trig.
It's like unlocking a hidden dimension. And speaking of hidden dimensions, this textbook takes us even further down the rabbit hole with its next example.
Okay.
It involves something that I think we've all probably played with at some point.
Oh, okay. Let's hear it.
Shadows.
Shadows.
Yeah.
That's a good one.
So they're not just for making funny shapes on the wall, are they?
They're not, no.
Yeah.
They actually hold, believe it or not, some really valuable geometric clues,
Okay.
especially when it comes to trigonometry.
Tell me more. What's the, shadow-related mystery we're tackling this time?
Okay, so imagine a tower, okay?
Okay.
This tower is bathed in sunlight.
Mm.
It's casting this long shadow on the ground. Now, as the sun moves across the sky,
Right.
the angle of the sun's rays is changing,
Right.
And so is the length of that shadow. So this example gives us a scenario. And in this scenario, the shadow of the tower is 40 meters longer when the sun's altitude is 30 degrees
Okay.
compared to when it's 60 degrees.
Hold on. Let me make sure I have all the pieces here before we start putting this puzzle together.
Okay.
So we have two different shadow lengths
Yes.
and two different sun angles.
Yes.
And our goal is to use that information to then calculate the tower's height.
That is the goal. That's exactly right.
That sounds challenging.
It might seem that way, but like any good detective,
Okay.
we can break this down. So the key here, visualize the scene.
Okay.
All right, so you've got your tower. It's standing tall.
Uh-huh.
Its shadow is stretching out along the ground.
Okay.
Now imagine those sun rays hitting the top of that tower at those two different angles.
Right.
What do we have? We have not one, but two right triangles.
Ooh. I see where you are going with this. So the tower itself is one side of both of the triangles. The shadow is like the base. And the sun's rays are kind of like forming the hypotenuse.
Yes, exactly. You've got it. And can we use the tangent again?
We can use the tangent again. I was just about to say it.
I knew you were going to say it.
I'm picking up on these clues now, I feel like. I'm like, Sherlock Holmes over here.
You got it. That's right. So we have the angles, right?
Yeah.
30 degrees, 60 degrees. And we are trying to find the opposite side, which is the tower's height.
Yeah.
And we've got the shadow lengths. And those are our adjacent sides for each of our two triangles. So we can set up two equations using the tangent, one for each angle, and its corresponding shadow length.
Okay.
A little bit of algebra, we isolate the unknown, we solve for that tower's height.
So it's like we're solving a system of equations.
Yes.
But instead of just X's and Y's,
Sure.
we're dealing with angles and shadows and the height of a tower.
Exactly.
I gotta say, I'm really starting to enjoy this whole trig detective role.
Right. And the best part is the mysteries just keep getting more interesting.
Bring it on.
Yeah.
What do we have next?
Okay, so from shadows, we are now ascending to new heights. Literally.
Okay.
Our next case involves not one, but two buildings.
Ooh. A multi-building mystery. All right, this does sound intriguing. What's the setup? Are we dangling from rooftops with protractors?
Okay, not quite as daring as that,
Yeah.
but almost as cool.
Okay.
So imagine that you are standing on top of an 8-meter tall building. You're looking across at a much taller building in the distance. It's a multi-story building.
Okay.
And using your trusty tools,
Of course.
you measure the angles of depression to the top and the bottom of that taller building.
Okay, so time for a quick little refresh on angle of depression.
Yes,
We're talking about it's the downward angle from our line of sight to an object below us, right?
that is correct.
Okay, just making sure.
Yes.
I'm visualizing it. I've got it.
Okay, good.
Okay.
So in this scenario,
Mm-hmm.
let's say the angle of depression to the top of that taller building is 30 degrees.
Okay.
And the angle of depression to the bottom is 45 degrees.
Got it.
Okay.
So we're trying to find out the height of that multi-story giant.
We are. That's goal number 1. And the distance between the two buildings.
Ooh. Okay, so we have 2 angles.
Yes.
We have the height of the shorter building, the one that we are standing on.
Yes.
We need to find the height of the taller building and the distance between them. Sounds like we need all of our trig detective skills for this one.
You do. But before we get lost in the calculations,
Right.
let's remember our detective work here. The key. Visualization.
Okay.
Picture those lines of sight.
Okay.
Okay, from your position on that shorter building down to the top and bottom of that taller one.
All right.
And see those triangles forming.
I do.
Okay.
It's like we've got the taller building, the distance between the buildings, and then like an imaginary line
Exactly.
connecting the rooftops. That's like our big triangle.
Yes. Big right triangle.
Right. And then within that, we have the line of sight to the top of the taller building.
That's right. You've got another right triangle. So you've broken it down,
Okay.
this seemingly complex problem, into manageable right triangles.
Yeah.
And now we can bring in our trusty tangent
Okay.
along with those angles that we have, right?
Mhm.
And the height of the shorter building. Set up a system of equations.
Mhm.
And we can solve for those unknowns.
I'm seeing a pattern here. It's no matter how complex it can seem,
Right.
we break it down into these right triangles.
Yeah.
Okay, we use those trig ratios. We find the missing pieces.
That's it.
And what's even more remarkable is that this isn't just about like measuring buildings, is it? Like,
Yeah.
like this is used in so many fields.
So many fields use this. We're
Yeah.
talking architecture, engineering.
Yeah.
We're talking navigation. Even astronomy uses these principles.
It's like from buildings to the stars. Like trigonometry really is the Swiss Army knife of geometry.
It really is.
But before we get too lost in space,
Okay.
this textbook has one more earthly example for us to unravel.
Okay, bring it on. Let's hear it.
Okay. This time, we're going to the banks of a river with a bridge standing sentinel above.
I like it.
And our goal is to figure out how wide the river is.
Yeah.
And I'm guessing swimming across with a tape measure is not an option.
Not really, no. Unless you want to be like,
Yeah, and by a shark.
yeah,
Yeah.
exactly.
But what do we do?
So instead, imagine you're standing on that bridge. You're looking down at the riverbanks. The bridge is 3 meters above the water.
Okay.
And you're using your angle measuring device to determine the angles of depression to each bank.
Okay, so let me just make sure I'm picturing all of this in my mind correctly here.
Okay.
So we're looking down from the bridge to each bank.
Yes.
Those downward angles, those are our angles of depression.
Yes.
And we are using those angles along with the bridge's height to then calculate the river's width.
That's it.
It's amazing how these concepts just keep coming back around. It's a recurring theme in a good mystery novel.
Right. You're catching on to the pattern here. Okay. So in this case, let's say the angle of depression to one bank is 30 degrees and 45 degrees to the other bank.
Okay.
Now, picture this. The width of the river. That forms the base of a big triangle.
Okay.
Okay. The bridge is like a perpendicular line cutting that large triangle into 2 smaller right triangles.
Right.
You got it.
So we can use the angle of depression, we can use the bridge height, figure out those other sides of the smaller triangles, add them together,
Exactly.
and then we've got the whole river.
You got it. That's exactly it. It's like we're piecing together this puzzle, and we're using those trigonometric ratios to find the missing lengths.
Yeah.
And you know what's really cool about this? This whole river measuring scenario, this is a great example of how trigonometry is used in surveying.
Oh, wow.
Right.
Okay.
Surveyors use these same principles. Obviously, they have much more sophisticated instruments.
Yeah.
But they use these same principles to map out land, to create boundaries, even to plan infrastructure projects.
It's amazing to me to think about like how something that seems so, I don't know, abstract. Like when you're a kid in school and you're learning these mathematical concepts, it can feel very abstract. And then to think about how it has such real-world applications, it's pretty remarkable.
It
It's
is.
like we've gone from measuring towers to mapping rivers and even touched upon the vast distances of space,
That's right. That's right.
all thanks to the power of trigonometry.
It really goes to show that math isn't just about, equations and formulas. It's a language
Ooh, I like that.
that helps us understand and navigate the world around us.
It's like a secret code.
It is.
to help us understand everything around us. That's really cool.
It is cool.
Well, I think that brings us to the end of our deep dive for today.
Wow, that's a good one.
It was a good one. It was a brain twister for sure. So for all of you listening at home, the next time you see a tall building or a bridge spanning a river, even just the shadow cast by a tree, I want you to remember those invisible triangles and the power of trigonometry that helps us make sense of it all.
I love that.
Yeah.
I love that. And who knows, you might even be inspired to, dust off those trig skills and try some of these calculations yourself.
I love it.
You never know.
Until next time, keep those minds curious. Keep those trig detective eyes open. You never know what mysteries you might unravel.